Okay, so good morning, everybody.
Good
I
morning.
would like to welcome you on the first webinar in a grant period 2. Today we will hear lectures or short presentations from 3 persons. First will be presenting Irena Berteli, STSM grantee, with her presentation FTIR and TGA analysis of resin and pitch mixtures used as adhesives in the past, understanding ancient technology and material aging.
Sorry for too long title.
No problem. I just have it on my back screen, so I had to look a little bit on the right. The second lecture will be by Elisabeth Johann, the tradition of large resin extraction in Austria. And the third one will be given by Jale Janik, utilization of biochar as a seed coating material. So I think, Irene, the floor is yours.
Okay, thank you. Let me show my screen. So, okay. Why? Okay. You can see it?
Yes.
Okay. So, good morning to everybody. Today I'm here to present you the topic of my short-term scientific mission, some of the results that I obtain, and in particular, how this grant could be a useful tool for our researches. But first, I would like to introduce my research team and my PhD project. So I'm part of the Schiebeck Research Group that is based at the Department of Chemistry and Industrial Chemistry of the University of Pisa, and it's part of our COST Action. And the main topic of our research team is the study of materials from the field of cultural heritage through the application of mass spectrometric based technique. So for what concerns instead my PhD project, I'm a chemist and I study archaeological adhesives. Natural resinous substances like resins, pitches, and tarts that are often mixed with other natural materials like waxes, oils, or inorganics. And of course, I studied this material with mass spectrometry in order to characterize, to study the chemical interaction between the component of these adhesives and obtain information on their resulting properties. So, due to the topic of my PhD project, I am part of the working group 2 of the COST, the one that deals with the analytical characterization, since January 2024. And being part of this COST gave me the opportunities to set my PhD project in a bigger and more dynamic context, and in this way obtain collaboration and also support for my research, like this STSM grant. And that grant was very helpful for me since helped me to effort part of my period abroad in Poznan and to be part of our second general meeting held, of course, in Poznan the last March. And I knew about this grant thanks to the periodic call for application of the COST, so through the website, by email, and also by talking with my colleagues in Pisa. So thanks to be part to be an active part of the COST Action. And but now I want to describe more in detail the project of this short period. So the aim of this research was to analyze the sample under consideration in my PhD project by applying infrared spectroscopy and thermogravimetric analysis in order to obtain additional information on the chemical composition of this mixture, and compare this data obtained with those I obtained through the mass spectrometry in Pisa, and also obtain more detailed information about the aging processes of this material. So for the team, my supervisor, Erika Ribechini, member of the COST, and I contacted the team, the research team of the University of Life Science in Poznan, in particular, Professor Magdalena Zborowska, our chair, since she's an expert of the FTIR on this kind of material. And she put us in touch with one of her colleagues, Professor Monika Barkowiak, I hope to say it properly, that she's an expert in the field of TGA. And our research team already works together, but this period was a further occasion to increase the bond between our research team. And thanks to this grant, I was able to cover 1 month of my staying in Poznan, where I was guested at the Department of Forestry and Wood Technology, the same department that hosted our training school and the second general meeting. So here I reported the instrumentation that I used in Poznan. So we have an ATR FTIR and the thermogravimetric balance, and I performed both these analyses on my mock-up samples that I prepared in Pisa, both fresh samples and naturally aged for 1 month. And here I schematized the working plan. So I started first with the analysis on the raw materials, since they are the simplest system under consideration. So in this way, I obtain the optimal parameters for the other analysis, and in particular, we obtained that we were able to directly analyze them through the FTIR in ATR mode. And we obtained the parameters for the thermogravimetric analysis, so the temperature, the optimal temperature of the maximum, and the heating rate. So after that, I performed the analysis on the mixtures, both fresh and preheated at 300 degrees, in order to observe if we were able to observe some differences in terms of thermal behavior and chemical composition. And lastly, I analyzed the aged samples to visualize the effect of the aging. So I want to discuss just some example of the preliminary results that I obtained. So here I reported the TGA curves that I obtained for a sample made by a mixture of resin and beeswax, the blue curves, and the same sample but preheated at 300 degrees, aged, and both heated and aged. And what we can observe? We can observe that the 3 pre-treated sample show a higher temperature value at the flex point. So it suggests that there's a higher reticulated fraction inside the samples. But also we can see that these 3 curves the profile is simpler compared to the curves of the fresh samples. So we can also say that the general complexity of the system is lower in the pre-treated samples. So I compared the results from TGA with those I obtained from the FTIR, and here I reported the graph of the principal component. So we can see all together all the samples, and we can observe that the preheated and aged are like collapsed to the center of the PCA. And that means that compared to the fresh samples and raw materials, they have lost the main spectral features. So this is also mean that they lost the main chemical structure, characteristic chemical structure features of these materials. In particular, through the FTIR, I was able to differentiate in terms of in structure the 4 raw materials. So here reported the spectra together with some of most important region for the differentiation. But I was also able to observe both all the contribution of the raw materials inside the spectrum of the mixture. So here I reported, for example, beeswax, pine resin, and their fresh mixture. And I was also able to observe the differences between the fresh and the aged sample. So thanks to these first preliminary results, together with the rapidity of execution of the FTIR in ATR mode, we decide together with Professor Zborowska to start a new set of experiment in order to monitor the aging process of these materials. So we started from the fresh sample and we let them aged for 1 month in natural conditions, and we perform periodic analysis on them in order to have the different step of the aging process. And together with that, we also decide to perform both the analysis, the TGA and the FTIR, on some of mine archaeological samples in order to compare the result that we obtain for mock-ups and the real samples, and also to check if this analytical approach works also in the real cases. So I can conclude that this STSM period was really fruitful for my PhD project, since I obtained really interesting preliminary results. And these preliminary works also suggested further experiments to enforce the results that I obtained. And so at the end, I spent 3 months with the colleagues of the University of Poznan. And that's it. Thank you for your kind attention.
Thank you for your presentation. And I saw that we have at least one question. It was from Panagiotis, and the question is, how did you choose the temperature profile?
The temperature profile for the TGA?
Maybe Panagiotis this if you can.
Yes.
Yes.
Yeah.
Okay.
Yes. About the TGA of the temperature profile for the TGA measurements. Did you read the literature and?
Since I work with Professor Barkowiak, she already performed several analyses on this kind of material, so she was aware which are the optimal parameters. So we just tried if they works with samples made by 2 or more components together. So we tried on the raw materials, but like oils, since she not usually analyze this kind of material, and they works. And now and after we test them with the fresh mixture to see if they works also in cases where two or more material were together.
So the temperature profile was ramping from ambient temperature to the maximum temperature that you had without
700, yeah.
700.
With
okay.
a heating rate of 5 degrees per minute.
Perfect. Thank you. Thank
you. And we have one question from Natalia. If you can.
Yes, you can see it here in the chat box. I only want to ask in how many repetitions this TGA analysis were made? How many samples were analyzed?
Since the number of sample is higher and the analysis takes, I can run just 2 samples per day. We made just one analysis for each samples.
Okay, thank you.
Do we have?
Yes. Can I ask an additional question regarding the FTIR analysis? The results obtained by the FTIR analysis was useful at the end. What was the outcome of the results for the FTIR analysis?
With the FTIR, I can see the differences between the most important fresh and aged samples in the chemical structures since the peaks, for example, increase, decrease, or shift. So in this term, it's more like a comparison between the different samples to see how the same sample after the heating pretreatment and the aging change the composition.
Great. Thank you very much. Thank you.
You're welcome. Thank you.
Do we have additional questions?
Maybe I have short comment.
Okay. Yes,
because I was a host together with Monika Bartkowiak, yes. So therefore, I have to say, I want to say that Irena's stay was very, very valuable to us, to our research team in Poznań at Poznań University of Life Sciences, because Irena performed a lot of good analysis of very, very interesting samples to us, yes, because this sample, this was a group set of different tars and pitches, yes, and mixtures. So analysis of this sample was very, very interesting for us. And I have to say that Irena came with a good idea for research, with good plan, and therefore we made a lot of things together. And to be honest, our team only had her a little, because Irena worked very, very independent, and and she knew what to do. And I hope that after this short, to us, too short trainings, is not training or only STSM, Irena will publish these results and with support of COST Action, of course, yes. And I hope that you will support COST Action with your publication, and you will use also maybe open access of our COST Action. So please think about this, that you can publish these results with support of COST Action.
Okay, thank you.
Thank you very much. Thank you very much for your stay in Poznań. Thank you.
May I ask a question?
Sure. Yes.
Yeah. I have a basic question. Where is the raw material coming from? I didn't understand that.
Okay, the raw material, I buy it locally. For example, the beeswax belongs to a friend of my father. And the resins I bought it at local store here in my village that is specialized in natural materials. And the peaches were made by colleagues with a traditional way. Okay.
So that was mixed together to make a kind of glue or something.
Yeah,
okay.
Because we have some archaeological adhesives already characterized, and we observe that are made of this kind of material. So pine resin together with beeswax and oil. So I prepared based on these results, I prepared my mock-ups.
Okay, thanks. Yeah.
Thank you.
Thank you for the presentation and the questions. Can we move to the next presentation or some additional comments from anyone? No. Okay, so now Elizabeth Johanni.
Can you see? Can you see my presentation?
Unfortunately not.
Now?
No.
No? Oh, what's the matter? Now?
No.
No?
No, we cannot see it.
Oh, this is the shame.
It worked a few minutes ago.
Yes. It worked?
No.
No?
No.
No. Whatever have I to do?
You should use the share button.
Yes, I did.
Yeah. Oh, now, yeah, we can see your screen.
Can you see the presentation?
Yes.
Wonderful. Yes, okay, it's working.
Yes, everything is okay now.
Thank you very much. And my contribution shows the wide range of the cost action, because now we are going back to the resin and where it's produced and how it's growing or how it is processed. The knowledge and innovations and practices of local communities have greatly contributed to the world's natural and cultural heritage by helping to sustain production of multiple goods and services that enhance livelihood, security, and quality of life. Many of these products are important resources in the context of renewable materials and bioeconomy. For several years, research in the field of wood chemistry are being developed based on the traditional raw material wood. And certain ingredients have already been used in the past. These include the wood extracts, wood oil, turpentine, and tar or resins. And in this chapter, we focus on resin, particular resin of Larch, extracted in the Alpine region and its application in local communities and beyond. And learning about the diverse production concepts of the past will not only point to the safeguarding of the cultural heritage today, but also to future strategies towards sustainable raw material supply. I will talk about the occurrence and location, the material and method I've used, the extraction of a large resin, which is very specific, the methods used throughout history, some products, discussion, and also some words about the intangible cultural heritage. Larch is a conifer native to Europe, growing in the Alps under up to the upper timberline, and it's growing together with spruce or with mountain pine, or also outside its natural range in mixed stands with common beech. And today its main habitat is the high altitudes of the Austrian Alps, the Sudeten Mountains, Carpathians, in Switzerland, in the French Alps, and in northern Italy. And the region where it's still harvested is there's some parts in Austria, in Italy, in southwestern of Switzerland. The sources I've used, the primary sources stored in the Carinthian State Archive, and some literature, but not so much. And but I also visited two enterprises where large palm is still processed. And I also made an excursion in the mountain forests where large resin is still extracted by a resin worker on behalf of the forest owner. There are two different types of resin. It's scratched resin, which is collected as resin that had dried on the tree and is scraped off with a knife or by hand, and the flowing resin, which is extracted by drilling in the timber trunk into the resin canal. And the flesh resin is then flowing out like honey. One of the oldest references that can be found is a scientific collection of the Roman historian and writer Pliny the Elder, and he describes large resin ointment for treating skin diseases. And large resin was also delivered from the Austrian Alps to the Roman Empire for sealing the ship planks. And this also has been mentioned in custom agreements between the bishops of Trentino and Brixen in 1202. And the first written report about this form of use, the drilling into the large stem, comes from Carinthia, from the Optak settle from 1391. From the 16th century onwards, resin harvesting was always under the control of the authorities. This was considered to be a sovereign privilege, and that had to be paid a collection fee, and it was an annual rent, or the workers leased a certain forest plot for a flat rate. And there were some contracts which granted also the so-called environmental friendly harvesting of the resin, and with regard to the payment, so the state could get some money in its pocket, and there was always a discussion if the immediate profit at once by renting to the resin workers should be the better system, or the expected future from the sale of the quality timber. And the state privilege of drilling large trees was only abolished in 1787 by Emperor Joseph II. Only from this time, the forest owners were allowed to drill in their own forest and sell the product. From the 1860s onwards, the drilling of large trees decreased because the price of quality large wood rose. And in 1930, there were still 14 entrepreneurs working in the region, and it became also more important during World War I. It became economically interesting again, and it lasted till the mid of the 20th century. And then it was a decline due to cheap imports from overseas. But larch biochar is still an interesting additional income to the farmers, and it's still extracted in some regions in Austria, in Carinthia, in South Tyrol, and in Wallis in Switzerland. There was, of course, a legal framework which wanted to regulate the harvesting and to minimize the environmental impact, and these the bans were included in the mining regulations, but also in the forest regulations dating back to the 15th century. And only in the 18th century, Maria Theresia in 1745 permitted to drill the large trees in those state-owned forests that could not be used to produce charcoal, firewood, or construction wood or boards. And in 1882, a law finally passed in Carinthia that dealt with the authorization to pick, pitch, and drill turpentine for the future. Some environmental some points were included in the leasing contracts, which were concluded between the resin worker and the state to avoid damages. So it was said that only in specific forest districts the resin could be harvested, or for a certain period, or it should be done as careful as possible, and the other regulations. But of course, the damage was visible. There were different methods used throughout history. Since larch forms vertical cracks in the tree trunk due to the tension during growing, which fill with the large resin, the extraction of this deposit can only be archived by drilling into these pockets. In this way, the so-called Venetian turpentine or laureate is obtained. Only the resin of European larch is suitable for further processing in pharmaceutical and cosmetics, because the resin of Siberian larch is not usable due to the higher acid content. And there are several factors influencing the resin production, such as soil, the health of the tree, the sea level. The best is between 800 and 1,300 meters above sea level. The diameter at breast at least should be 35 centimeters, and freestanding trees in sunny sites usually yielded the greatest amount of resin. In ancient times, large resin was originally extracted by shepherds. They used an axe to make deep holes in about 1 to 2 meters above ground in the bowl until the resin cracks were opened and the resin could flow out and could be collected. It can be assumed that the first attempts to extract had negative impacts on the health of the tree, and in worst case led to the dying of. And later on, about the so-called Styrian method came into being and lasted until about 1850. And in this method, the bowl was drilled diagonally upwards into the resin crack, and just below the mouth of the candle, the so-called drip rod was inserted into the notch in the bark, which facilitated the resin flow down to a container underneath. You can see it on the right-hand side in the picture. And the drill holes were not plugged, and the candle generally remained open during the resin producing period. This had fatal consequences because the open borehole opened to infection by fungal spores, and the trunks visible suffered. And the resin flow lasted from 6 to 10 years. And later on, the holes were plugged with a wooden plug, and then the yield was lower, but by half. But the resin could be extracted for more years, up to 30 years. And later on, the so-called Tyrolean method came into being, And now the logs were drilled in spring over 15 to 20 degrees upwards. But the hole was plugged immediately, and the resin was collected in autumn. And then after the collection, the holes were plugged again. And this so-called Tyrolean method came also into being in Carinthia and Styria in the second half of the 20th century. And the technique was improved again, and there were two persons. One was Nicola Schuster. He was an entrepreneur who processed the resin collection by the farmers around. When he became aware of the harmful impact, his achievement was to refine the extraction method to such an extent that if a certain criteria is met, the tree is not harmed. And already in 1919, he wanted to scientifically accompany the resin utilization project and asked for support at the Research Institute in Vienna. And together with Dr. Schmidt, he was the later director of this institute, they developed a method of extraction of large resin that avoided damage to drill the large trees. And it was now drilled from outside upwards, and the hole was closed immediately and only opened when the resin was collected, and this was usually twice a year. I've brought you some pictures which I took recently just to see the method. Here you can see how it's how the borehole is done diagonally upwards, and it's only just above the soil, above the ground. And here you can see this, and the prop is only opened when you harvest the resin, and it's closed immediately, as you can see. And in general, the first resin harvest can start just a few months after drilling. And you call the resin, the first resin is called virgin forest. Here you can see how it is done. It's taken out with a spoon and put in a pot. You can see it here as it's done. Mm. And then it's put in this can. And this is special. So. And then the wooden plug is carefully hammered back, and the tree is marked. And the resin extraction generally takes place in a 2 years interval. And from a donor tree, you can harvest 200 to 370 grams of resin per year. And the most productive time is the first years after drilling, and then the harvest is less. The processing of resin takes place in the area, and after the first cleaning through a sieve, the resin is filled several times, slightly heated and refined by steam distillation, and the raw larch resin is converted into large turpentine by decanting. There are very simple mechanism who take this. But also that this is done in this sawmill. They have it as a side income, but also they are sophisticated and more well-equipped laboratories also in the region. The products, larch palm is used in natural and porcelain paints as a binder for paint production, as the plasticine elastic varnishes, and as an active ingredient in pharmaceutical and cosmetic products. And due to its optical properties, Venetian turpentine was of great importance in the past for a long time as a potent sealant in optics. It is considered considered particularly valuable in folk medicine because of its preserving and healing properties. Here you can see some products, even chewing gum is now used. And records with regard to the folk medicine, records date back to the 16th century, and farmers often made this product by themselves and used it against pain. And it was also used against rheumatism, sprains of catarrh, and with good results. It was also in the 1700s, there are ointments mentioned and plasters to clean old and new wounds. It was used internally, cleansing the lungs, and diuretic, and externally, especially by surgeons. And they also used it for the husbandry, for the hoofs of the sheep and the goats, and also, of course, to seal wooden barrels and for caulking in boat and ship building. Turpentine oils are still used today, both industrially and therapeutically. It has special properties that make it a high-quality natural raw material for many technical fields. It is used in chemical industry, but of course also for violin, bow, resin, then in optic industry, in cosmetic and fragrance manufacturers, in artist paints, and an antiseptic and circulation stimulating effect. Today it's only used external to relieve pain and stimulate local wound healing, but it's also often used in veterinary medicine. Some discussion. There may have been regional overuse of large stands in the past as a result of the ancient applied methods of extracting. Thus, a prevailing belief still exists that the extraction of resin damages the tree by declining their health in promoting insect infestation. This argument doesn't consider the technical improvements which has been introduced since the turn of the 19th century. And this goes back to the fruitful collaboration between practice and science, and thus the negative impact on large trees does not happen anymore. And this is scientifically proved, and due to a lot of research done by the Maria Forest Research Institute. And according to the report of some sawmill owners, a certain improvement in the quality of wood can be perceived due to the natural closing of the resin canals after the resin has been extracted. And I come to the end, the cultural heritage. In 2018, the craft of extracting a process in large resin was included in the national list of the Austrian national list of UNESCO. And it's a technique of collecting which have passed down in the families through the oral tradition for generations. And it's with regard to the experience, with regard to wind direction, main axis, exposure, diameter of trees, and depth of the borehole. And in addition to the special techniques, local farmers and resin workers own expressions and specific tools used for extraction, and this is also part of the element. And with regard to the marketing, an increasing number of farmers extract the resin in their own forests nowadays and also process it to ointments themselves. And the Austrian resin companies supply their natural cosmetics to health resorts, thermal baths, and pharmacies in Austria on a small scale. However, the majority of sales are made directly from the company and via mail order. Thank you very much for your attention. So I'm at the end.
Thank you. Thank you for the interesting presentation. It's very interesting for me that you can produce this resin in a small scale, and despite the large industries which now import the resin from the other countries in the Central Europe, but you still manage in Austria to produce it on a small scale. I found it really, like, maybe we could also do it in Poland one day.
Yeah, but it depends on the because larch, European larch is not growing on a wide scale. It's only a limited space where the soil is good for growing and so on. And this is the reason why looking to Central Europe, it's only really a small space in Italy, in Switzerland, and Tyrol and Carinthia. So it's very limited space, and I think this is also the reason why, because it's if you look at the internet, there's a lot of demand for large resin, like this,
Yes.
and the balm and. Because
we have question from Silas.
Yeah, dear Elizabeth, thank you very much. Can you hear me?
Yes.
Yes, I just have one quick question because I'm doing research on historical recipes containing tars and resins, and I came up with there's some confusion regarding the names. So I have the feeling like in Lower Austria, Southern Germany, and Bavaria, Tyrol especially, the German word Pech is used synonymously for everything like the resinous part collected in the tree, while up in the north of Germany and further up north of the Alps, pech and pitch is more used for destructive distillation of wood, for tars. Is there a certain regional speciality to this confusion of nomenclature? Is there a tar production in the area? Yeah.
For a long time, it was used. Pitch was used for everything, like this. Yeah.
Yes.
And also in the language people used. It's just pech. It was not used for the flowing liquid from resin.
Okay.
But if you harvest it from the tree, just scratching out, then it's also called pech. Yeah. Even it's resin.
Yeah.
It's also in the literature. It's always a mixture.
Yeah.
Also in German language, it's also in my home countries. It's always and so it's difficult. Pitch, pech, and resin, harz, and then balm, large balm. It's also balsam. It's also used for this. So it's you have to look very carefully because it's sometimes pitch is for everything.
Yeah. Thank you very much.
Yeah.
Thank you for the comment. Do we have any other questions?
Maybe one small question, because I didn't saw it. Maybe it was in this presentation. What's the scale of this small production in this region? Can you tell us? I don't know, in kilograms, in tons, in people who are producing it. What's the scale?
Yeah, it's only as well as in Italy or in Switzerland, as in south of Switzerland. It has nearly has been distinguished, no? But there were some people who tried to maintain it because of the high quality of this product, and it's only a small group. It's and it needs that attention is paid on this, and if there's a demand, also nowadays there's a demand, and there are several farmers who started again with harvesting, but with this improved technique that it's no harm to the trees. And I know a forest owner who is very careful with his forest, and he's president of ProSilva, and he also has some forest stands in his own forest where this harvesting is done. It's a sideline income, but it is an income also for the farmers still, and probably with a trend to natural products, it will increase. But there are only certain stands between 800 and 1,200 meter which yield enough resin that it can be harvested. It's a limited area, so it's a very special product also in the context of the cost action. Yeah. So because they sell it on their own, there is no statistic telling you how many kilos you can are produced. I did not find any statistic about this, about the amount of harvest. You can say it depends how many trees you can harvest. So I have in my presentation how many trees you can harvest per person and per year, how many trees you can drill. So it also depends also from the available human workforce.
Okay, so maybe I will ask in different way. Is it stable, or it's increasing or decreasing this amount? Because I'm asking, it's ecologic, it's let's say it's European, yes, it's this very nice kind of production when you don't harm the environment, but you can take something really good. And that's why I'm asking if there is some increasing, let's say, amount of people who are interested in it and want to do it, or no, it's some kind of traditional production which is only it's not increasing, but it's, let's say, it's stable or even decreasing.
For my opinion, it's increasing, but because there are some young people who started this harvesting for again. Yeah, their fathers didn't do it, but they harvest in their own forest, and many of them, or some of them, they are producing their own healing ointments and selling it via internet. So I think it's increasing, and particularly since 2018, when it became part of the Austrian national list of UNESCO. More attention is paid on this kind of forest use, which of course is always a side product, yeah, and non-wood product. So it has never been in Austria, and also in this region, never been the main income for the forest owner. Never. It was always a side product, because this was always on a small scale and not a big factory. Some in the 19th century there was a manufacturer in Innsbruck, and they sent several resin workers out in the forest to harvest it, but it never was a big business, because the space it's limited. Yeah.
But it's great information that there are still a lot of people who are interested in it, that it's not dying, but as you tell us, it's increasing. Great.
I don't think it's dying. No.
Of course. Therefore, we have this action.
Yeah.
I see also the hand from Yale.
Yes. Yeah, Jakob. Okay. Dr. Johan, can you say a kilogram per farmer per year?
Yes, I can do it. Wait a moment. I have it in my thing. Yeah. That's to say the right words. Also, up to 3 kilograms of resin could be extracted by trunk over a period of 25 to 30 years. So this means per year 0.1 kilogram.
Okay, thank you. Thank you very much. Thank you very much.
Yeah.
Thank you. And on the chat, I think it was similar question, right? Yeah, how many grams can be collected per year? So it's already answered. And do you have any comments? to this lecture. Okay. So thank you, Elizabeth, for really nice presentation. I find the resin collection really interesting myself. So
thank you for giving me the opportunity to talk about my research. Thank you very much.
Thank you. And now I would like to ask Jale Janik to present her presentation. Now we will change from resin and pitch to biochar.
Yeah. Is seen?
Yes.
Is okay?
Yes, everything.
Hello, is okay. Hello, everybody. Within the scope of the COST project, we are working on biochar, not charcoal. Today, I'm going to talk about the use of biochar in a different area, a seed coating material. Before explaining our experimental and results, I would like to give short information on plant growth promoting rhizobacteria and seed coating. Rhizobacteria is root associated bacteria. Plant growth promoting rhizobacteria is able to colonize the root and is beneficial for plant growth and development. In future, they are expected to replace the chemical fertilizer and pesticides. And these bacteria are used as used as biofertilizers and biocontrol agents. Several strains bacteria are commercially available as dry powder, suspension of in oil and liquid form products. Now, coming to seed coating, besides plant growth promoting bacteria, seed coating is considered one of the best methods to promote sustainable agriculture. Seed coating making seed shape, size, weight, and seed surface more uniform to make them easier to plant. Seed coating is a mechanism of providing plant growth promoting substance with seeds to improve seed quality, the protection to different kinds of insect, pests, and fungi. A broad range of materials in processes of seed coating are used. According to material functions, these materials can be generally categorized in three classes: binder, fillers, and active ingredients. Binders and fillers are used to provide for the thermal, physical, and mechanical characteristics of coated seeds. Generally, natural and synthetic polymers, for example, methylcellulose, carboxymethylcellulose, polyvinyl alcohol, and gum arabic are used as binder. The fillers are popularly bulking inert materials and allow for physical modification, which is commonly used in the process of encrusting and pelleting. The most commonly used fillers are bentonite, lime, diatomates, and talc. Okay, Now, coming to biochar. Recently, seed coating with biochar has received much attention due to its ability to benefit plant productivity and microbial inoculants. As a seed coating material, biochar is a desirable and cost-effective carbon-generous substance. Here, this manuscript reviewed currently published studies on the roles of biochar in seed coating. Another subject is seed coating with plant growth promoting bacteria. As known, the seed industry is moving toward a greener future, and exploring microbial coating is one of the alternatives. The left side is an example of root without the bacteria, and the right side is an example with bacteria. Microbial seed coating is one of the alternatives to reduce the use of agrochemicals in sustainable agriculture. Apart from the microbial inoculum, seed coating formulations consisted of carrier materials. Most of carriers are organic, inorganic, or synthetic compounds. Cost, safety, environmental awareness, and availability are the key factors influencing the carrier choice. The most important risk in practice is the short shelf life of coated seeds with bacteria. Okay, let me talk about our experiments. We produced the biochar by two ways: dry carbonization and wet carbonization. In our studies, we used the pine sawdust and the waste dried fig. Sawdust is a byproduct of various woodworking operations. Waste dried figs contain aflatoxin, and they are disposed by incineration. In my country, we export the dried fig, but during drying process, some contamination is occurred. The main contamination is the alpha toxins. Because of this, we wanted to use these waste in biochar production for sustainable management of these waste. Pyrolysis in dry carbonization was carried out under nitrogen citrin at two temperatures, 350 and 600 degrees Celsius, for 1 hour under nitrogen citrin. Biochars were defined in the order of B, feedstock type, and carbonization temperature. For example, this B SD 350 corresponds to biochar produced from sawdust at 350 degrees Celsius. In wet carbonization experiments, we use the hydrothermal carbonization. In this experiments, the sawdust and water are mixed and carbonized in an autoclave under autogenic pressure at 200 degrees Celsius for 1 hour. In our experiments also, we produced activated carbon from sawdust by using chemical activation. In chemical activation, we used potassium hydroxide, and temperature was 700 degrees Celsius. Okay. In our study, we investigated whether produced biochar can be a suitable carrier for seed coating, which selected the bacteria, namely Bacillus and Chilonesis. The first is gram-positive, the other is gram-negative bacteria. Although most previous studies have reported that biochar can enhance soil microorganism communities, the effects of biochar on different microorganisms can be quite different. The composition and physicochemical properties of biochar obtained from different biomasses have differences, and thus their effects on organisms should be different. For instance, researchers observed an improvement of microbial growth when using poultry litter biochar, whereas they observed an inhibition of the same by fine dust-derived biochar. Biotoxicity test is a critical to use biochar as a microorganism carrier. For this reason, we performed a cytotoxicity test. Here you see the very schematic schema used cytotoxicity test. In this test, the biochar extracted with water for 20 hours. Meanwhile, the bacteria culture incubated and growth at 27 degrees Celsius for 24 hours. And both biochar water extract and the fresh bacteria culture mixed and every 2 hours, every 2 hours, the solution, 1 milliliter of solution was withdrawn and by pipette, and the number of bacteria colony were determined by using UV. As you see, this one sample to obtain the graphics from UV measurements, and from UV UV results, we calculated the number of colonies by increasing of the time. If the curve, this curve, is parallel to the control curve, it indicates that the biochar is not toxic. The other test we used, shelf life test. The shelf life test examines how long a bacteria remains safe and effective under certain storage conditions. The bacteria culture was prepared by incubation in a petri and then added in a saline water. Then the biochar and the saline water culture mixture mixed, homogenized by a sterile lock. The mixture was placed in a plastic bags, and these bags storage at a room temperature, and viable cells were counted at initial and monthly intervals for several months by plate contact methods. Okay, let me show some properties of produced biochars and activated carbon. The main physical-chemical characteristics of biochars that would be suitable for microbial inhabitation and growth in soil, including high porosity, efficient water holding capacity, appropriate carbon content, functional groups, and nutrients. Here you see the results. Here is seen the biochar from wet carbonization is acidic characters, and the activated carbon and the biochar obtained from blend, also more basic character, but the biochars obtained from sawdust, almost we can say neutral characters. Also here, what is the importance? The ratio of oxygen to carbon. This ratio indicates that the biochar surface is more aromatic and more hydrophilic. According to European Biochar Certificate, the ratio of hydrogen to carbon value must be less than 0.7 for the stability of biochar, and our all biochars, yes, the lower hydrogen to carbon ratio than European standard. Also, inorganic elements are very important for the agricultural use of biochar. Elements such as nitrogen, phosphorus, potassium, calcium, magnesium provide nutrients directly to plants for plant growth. Zinc and copper support plant growth, but nickel and zinc are inhibitors of some enzymes. Also, excess nickel may have a toxic effect. As you see, the biochars obtained from blends, sawdust plus waste dried pig contains high amounts zinc, high amount iron, and high amount potassium. The canals and pores on the biochar surface allow the large surface area with several possible locations useful for microbial attachment through physical and chemical interaction. As expected, the activated carbon has the highest surface area. And also biochars obtained high temperature, 600 degree, higher surface area than the biochars obtained low temperature. And also for compression purpose, we put the values of textural properties of chitosan. Chitosan is the commercial carrier, microbial carrier. You see, most of our biochars has higher surface area than commercial carrier. But I have to notice that the pore volume and pore size. Pore volume and pore size of commercial carrier is exactly different from our biochars. Here you see some images from our biochars. Carbon stability, we also measured the labile and stable carbon contents percents in our biochars. Carbon stability allows biochar to remain in the soil for a long time. Labile carbon refers to unstable carbon. High stable carbon content is ideal for long-term carbon storage. The amount of labile carbon is related to volatile matter, and labile carbon is rapidly metabolized by microorganisms and provides short-term soil fertility. Okay, now in this slide you see the toxicity results of our biochars. Most of biochars are non-toxic. Even also, this biochar promoted the microbial growth, but two of them is toxic. It is interestingly, for example, in case of biochar from sawdust obtained at 350 degrees Celsius, is toxic for Bacillus bacteria, but non-toxic Phyllonesis bacteria. In contrast, biochar obtained from wet carbonization, non-toxic for Bacillus, but toxic Phyllonesis for Phyllonesis. Actually, the relationship toxicity and biochar properties is not exactly clear, but generally is known that polycyclic aromatic hydrocarbons, PAH, in biochars play an important role in biochar toxicity, and their concentrations are specified. Concentrations limit are specified in the standards. The European Biochar Certification Standard, International Biochar Initiative, and United States Department of Agricultural Standards. But it should be noted that these standards are for the use of biochar in soil. We determined the PAH content of our biochars, which was toxic for Bacillus bacteria, and the results show that the biochar contained totally 1.9 milligram per kilogram, and is less than the limits. We continue investigated the reason of toxicity for this biochar. And also the biochar, remember, obtained from wet carbonization was non-toxic for Bacillus bacteria, but toxic Phyllonesis bacteria. To investigate the reason of toxicity, we washed biochar with water, because after wet carbonization experiments, the biochar separated from processed water by filtration. We directly filtrated and separate the biochar. Then the right used as biochar. In our to examine the toxicity reason, after filtration, we washed our biochar with water, and the result was surprise. After washing, all the biochar are non-toxic for all bacteria. To explain this reason, we analyzed the processed water and washing water, and we saw that the processed water main contents in processed water is furfural and phenolic compounds. These compounds, as known, are toxic for microorganisms, for bacteria. And to test the remove all these compounds, also remind on biochar. After washing, also washing water were analyzed, and as seen on this table, the washing water contains significant amount of phosphorus and phenol. And decided that, okay, in case of biochar obtained by wet carbonization, can be non-toxic after washing. Yes, here see the results of shell life test. Although 5 studies reported biochar is alternative microbial carrier, the mechanism of microbial interaction with the biochar surface is yet to be explored. But here one can easily say that the gram-positive bacteria, Bacillus, is more resistant for a long time than Kilonensis, gram-negative bacteria. The reason is like so, gram-positive bacteria, general gram-positive bacteria form spores. That means resistance to drying, low nutrient contact conditions, and the other stress conditions. However, the gram-negative bacteria do not form spores, so their storage stability is lower. But gram-negative bacteria shows as a good activity. Okay, our results, for example, is also interesting. The same biochar, for example, BSDF 600 biochar. This biochar shows good survive time for Bacillus bacteria, but not good Kilonensis bacteria. About after 3 months, all the bacteria dead. And similarly, for activated carbon, the Kilonensis bacteria was dead after 3 months. The study is still ongoing. Now we are trying to understand the relationship between toxicity, short shelf life, and physicochemical properties of biochars, and also We will test the seedling emergency test for biochar bacteria-coated seeds. Thank you very much for your attention.
Thank you for your presentation.
A little bit different subject than that of the groups.
Yes, but biochar is really strong in our action.
Yes, yes, but the biochar is more popular subject today.
Yes.
More popular.
Do we have questions?
Maybe I will ask because I understood that the toxicity of the last from biochars were checked that the furfuras were in high amount, yes, of water after filtration, this biochar, yes? Did I understand
Yes.
it well? Okay,
Yes,
and did you check if other biochars also had this furfuras, or you only checked this one which has high toxicity?
Yes, because this biochar, moment, you see?
Yeah.
This
Yes,
biochar,
yes, yeah.
These biochars obtained by wet carbonization. That means the biochar, after reaction, biochar was inside the process water.
Yeah.
And of course, the compounds process water also absorbed on the biochar here.
Yeah.
But in the dry carbonization, the process is exactly different. During carbonization, all volatile compounds goes outside, not accumulated on the biochar. And also, in the at the beginning of my speech, I said that the biochar, not charcoal. If biochar is produced under controlled conditions, and all volatiles like katran and tar, not remain on the biochar, goes out. Because of this, don't need the washing the other biochar. I have only one biochar that obtained by wet carbonization. Any question?
Yes, I understand that this was the only one which was from this type of carbonization. I agree. But I only ask if you are sure that the problem were furfuras, or is it only your suggestion, let's say?
Oh, yes, the general knowledge, the phenols and furfuras is poison for microorganisms. It's the general
Yes,
knowledge.
okay, I understand. But did you, for example, check if you remove this furfuras, for example, using some kind of filtration or something like this? This, if making, how to ask you, are you sure that if you remove this furfuras, this biochar won't be toxic? Are you sure?
Yes, because moment, after washing, the biochar was non-toxic for both bacteria.
Okay, that's what I was asking. Okay, I didn't saw it before. Okay, thank you.
Okay.
Thank you.
Thank you.
We are almost at
Finish.
the time, but if you have one more question. we still have time for that.
Yes, please. Just one question: Is it only at this coating technique? Is it only at the research level, or is it already in use somewhere?
Yeah, already in use. The coatings, seed
Okay.
coating is already in use, but the biochar coated biochar containing plant growth bacteria is the first time, just lab scale.
Okay. Thanks.
As I said here, the coated seed is already used, but the risk in practice is the short shelf life. We wanted to use the biochar as carriers to longer shelf life.
Okay.
But the correlation between properties of biochar and the shelf life is not clear. Explanation is very difficult because each bacteria has own properties like this.
Okay. Thanks.
Okay, thank you. And I would like to thank all the presenters. And now I will stop recording, but we'll have some informations or reminders for you also.